Good morning. So today is phase plane time. So we have last class work on two-dimensional systems, so two ODEs of first order, but they were linear. So that was necessary because we need to understand how to actually characterize a fixed point. And this is a very good idea. We start with a linear system. Right now, based on that knowledge we have acquired, we can actually then tackle the nonlinear system in two dimensions. So how a two-dimensional system looks like? So we already know that we have two variables. So in this case we can call it x dot 1, x dot 2, and this is similar to what we had last time. We were talking x dot y dot, so just two variables, and in the right hand side we have the nonlinear function, which can be function of both x1 and x2. So if we want to make a compact notation, we just use the bold in such a way, the bold notation. So the idea is that we will understand how this fx looks like. And the first thing we have to do is just to find the fixed points related to fx. So if you remember again, the linear system we were investigating last class, how many fixed points did system have? One fixed point, because we have just one crossing, one root of this linear function. Right now we can have n, like an n amount of fixed points, and this is gonna be somehow this is gonna lead to a zoology of fixed points. So not just one, but many of them, and they can have different properties. So in this case we can have, for example, a repeller. Then we have here a given saddle, like a saddle node. We could have eventually a repeller somewhere. We can have additional objects which are not actually fixed points but are actually limit cycles. So there are many things that can actually happen, and the somehow collection of these fixed points and the corresponding trajectories between them is what will create the big picture of the phase plane of the system. So as I already said, we have something else. In addition to fixed points, we will have closed orbits that are also recognized as limit cycles. We will see that in the next class. We did already this exercise, if you remember, in the second class when we were talking about one-dimensional systems. We wanted to have like uniqueness of the solution. So you remember, we had this x dot plane, and a given point in this, like in a given trajectory, has to lead to a future state, only to one future state. We cannot have two or three different possibilities because that would be an ill-posed problem. And in that moment, we were already able to derive the condition on when to have a well-posed problem. For that, we had to have an fx, so the function, and the corresponding derivative to be continuous in the region of interest. And this is somehow analogous now to these requirements for the existence uniqueness of the solution. So this is the initial value problem. So we have an initial condition, and we then need that the function f is continuous and also the partial derivatives are continuous, and this is going to happen in a region of interest. and also not only in a region of interest, but also in an interval of interest. So if we have this and this, and f being continuous and also the partial derivatives, there we are in the safe region. So we can actually have the following. We will have the advantage in the analysis that trajectories never intersect because solutions are unique, which again, it means that we don't have trajectories that crosses, and this is what is very nice. Imagine, as I showed you just before, we have this limit cycle. We just have a closed orbit, just call it closed orbit. And you just position yourself a point inside. So this point will also, as time elapses, will move into the phase plane. But this trajectory, this particle, is not allowed to go through this closed orbit, because in that moment we will have like a violation of this uniqueness of the solution. Therefore, the trajectory must remain confined forever. And this is what makes this phase plane a very attractive strategy to study nonlinear systems, because you can actually have like portions in the phase plane that can be well understood. Note also that you can actually approach the orbit, but it has to be in a very smooth way. So we will see also that you can have like spirals, little by little, approaching until arriving asymptotically to the limit cycle, in that sense. So you can actually reach the limit cycle, but in a very smooth way and almost like tangentially, if you wanna understand it in that way. So as I said just at the beginning, we need to understand the phase plane like locally, because we have this zoology of fixed points. So the idea is to isolate each fixed point and understand what is happening close to this fixed point. And for that we need linearization with respect to those fixed points. So you can actually go back to the slides of the second session when we do this together for just one dimension. So now we have two dimensions, but everything is basically the same. We have the perturbation, so the fixed point plus a perturbation, fixed point plus a perturbation, and we know that by definition we have f and g being 0 at the fixed points. Similar again to the 1D case, then we just make this connection, and we know that if we have a change, if we have a dynamics in this x, is because we have a dynamics in the corresponding perturbation. Remember that these quantities here and here, they are just 0, because a fixed point does not move, it's just static. Then if we have a change in x, it's because we have a change in the perturbation. And again, similar to the 1D case, we do a Taylor expansion. Right now it's going to be a two-dimensional Taylor expansion. So we have fx, and then we have these two terms. So now things are simplified because these terms are 0. Therefore, we have only these 4 derivatives. And if we collect the whole thing, we realize that this is nothing but the Jacobian. So the dynamics of the perturbations of x, so x ball, which is x and y, is just given by analyzing the Jacobian. And this Jacobian is actually defined at a given fixed point. So if we have a system with 3 fixed points, we will have to analyze 3 different Jacobian matrices. And these Jacobian matrices are analyzed in exactly the same way we analyze this A matrix we had in our last class for two-dimensional linear systems. Okay, And something to say related to this sentence in here. Imagine you solve this the eigenvalue problem for this matrix, and you realize you have two eigenvalues, and one eigenvalue is positive and one eigenvalue is negative. Then you automatically can say, this fixed point, so the Jacobian around that fixed point is telling me that this fixed point is a saddle. In the same way, you can say this is an attractor, this is a repeller, okay, or even a spiral, for example. But what happens if the Jacobian is telling you you have a center? Remember that a center is when you have the eigenvalues being purely imaginary. Okay, so this completely circular orbit, like the same that described this pendulum. In that moment, you should be aware that you obtain that result because you have ignored the high order terms. So if you include the high order terms in the analysis, you may realize that you reality you do not have a center, but you have actually a spiral. So these are like limiting cases that you have to be careful. Okay, so let's go with our first example. We have this system of equations. So the idea is that we will just find the fixed points, and then we just find the Jacobian of those fixed points, and just we make an analysis based on the phase portrait. Okay, so let's do this together. What is the first thing we have to do again? We have to equate these equations to 0. So we have minus x plus x to the cube equal to 0, and minus 2y equal to 0. We want to find the fixed points, no? So fixed points, you already have perceived that we have one fixed point, which is y star equal 0. Okay, because this is just the solution of this equation. Now, for this equation, we can just make things simpler when we factorize, which means that we will have x is equal to x to the square minus 1 equal to 0. Which leads to have a fixed point x star equal to 0, and the other one x dot equal to what? Equal to 1. Is it correct? Actually equal to plus minus 1. So we can have the two signs. So how many fixed points do we have? 2? 4? Actually we have 3 fixed points. We will just put it in here. So the first fixed point is x star 0, y star 0. The second one is x star 1, y star 0. And the third one is x star minus 1, y star 0. Okay. So we have found the fixed points. What do we do now? We actually compute the Jacobian for each fixed point. Okay, so what is the Jacobian? So just let's go easy. And what is fx in here? Yeah, is minus x plus x to the cube, and g of x is yeah, minus 2y. How is the Jacobian defined? Remember, Jacobian is equal. So normally I ask a question and someone answers all the time. So please remember from your classes of calculus. Yeah, okay, I already showed you as well. So is the f, the x, the f, the y, dg, the x, dg, dy, okay? And where this is evaluated at the fixed points. So let me just first derive, or let's say obtain this term in here. So how does it look like? So the first term is, yeah, minus 1, yes, plus 3x to the square. Here is, yeah, 0. Here is, yeah, 0. And in here we have minus 2. Great. Okay, now that we have the Jacobian, we can have the actual matrices for each point. So the Jacobian at 0, 0 is equal to what? Yeah, minus 1, 0, 0, minus 2. The Jacobian at 1, 0 is equal to what? Minus 1 plus 3. Minus 1 plus 3 is equal to 2. 0, 0, minus 2. And the Jacobian at, yeah, minus 1, 0 is equal to what? Again, no, the same thing. So this is what we have now. We have 3 values of the Jacobian, and each Jacobian matrix is associated with one fixed point. We have everything to build or to draw the phase portrait. So here with white, let's put it with blue, and then here like this. Like this. Okay, so we have the two axes. We have x and y, and the first thing we have to do is to just position the fixed points. So the fixed points, we know that are at the origin 0, 0. The other one is, yes, 1, 0, and the other one is, yeah, minus 1, 0, like this. Now we have to find, for each Jacobian the eigenvalues and the eigenvectors. This case is actually simple because, as you realize, all matrices are diagonal, which means that the eigenvalues are nothing but the elements of each diagonal. So I'm listening. If we consider this one, which have which eigenvalues? Yeah, we have minus 1, minus 2. The eigenvalues of this one is 2, yeah, and minus 2. And of this one, the same, 2, minus 2. And also we know that the eigenvectors of this matrix is just x and y. So this is going to be the vector. Let me just put it in here. So the eigenvector is going to be just 1, 0, and 0, 1. And it's going to be the same for the other cases because they are also diagonal matrices. Very good. So we stand at the origin and then we will just draw the first eigenvector like this, and it's telling me this eigenvector is associated with an eigenvalue which is -1, which means, since we already know from the last class, that any perturbation will grow with the growth rate being lambda, and the growth rate here is negative, so it's gonna be actually decaying towards the fixed point. So we have here something like this. Now if we go to the second eigendirection, is 0, 1, so it's actually aligned with this y-axis, and it's also related to an eigenvalue which is negative, so it's -2. And if you realize as well, this perturbation will go or will move faster in the y direction than in the x direction, because the absolute value of this lambda is stronger than this one. Okay, we have the first eigendirections. Now we move to this one in here, and we say, yeah, okay, we start with the first eigenvector, so it's gonna be the same one, 1, 0. So it's gonna be in here, and the eigenvalue related to that eigenvector is 2. So it means that it's an attractor or a repeller in that direction. It's actually a repeller. So this is going away from this one. And if we go to the other eigenvector, we find the same growth rate, which is -2. So it's an attractor in the y direction. And we can do the same for the third fixed point, which is -1, 0. So it's exactly the same Jacobian and the same eigenvalues. Therefore, we just actually maybe do copy paste from the previous one, from the one of the right. So we get something like this. Great. So we have now let's say the bones of the phase plane, the structure of the phase plane. Now what we have to do is just to fill the gaps by having some analysis, some intuition. So let's draw it with the yellow. Now if we are in this position here, where do you think the particle will move? To the right, to the left? I mean, not at all. It's gonna actually follow the direction of the closest eigendirection, which is this one pointing towards this origin. So it means that we will move in this way, and you can actually just go all the way until the origin. So it will go like this, and only when it gets very close to the other eigendirection, it moves like this. So the same thing happens in here, and so on. So it's symmetric, as you see, so it's gonna be the same for the other side, and so on. Now if we go very close to this one, let me just put this a little bit longer. If we go close, then it's gonna, well, basically nothing changes. It just goes in this direction and then move to the right. So you see that actually these two branches, the one going out from this node coming into this node, they are actually, there will be connection in there. So we have a saddle node connection. Well, you can just guess what is gonna happen in the rest of it. So it's gonna, if you are having a point in this one, then there is no way that this point goes to this origin, because you are somehow, you have this so-called separatrix. So it's gonna be like a boundary you cannot cross. So the particle is gonna just move along this one, but then when it arrives here, it just go out, like out from this fixed point, and so on. So for the sake of argument and not to have confusions, I will just plot the whole thing. Okay, so I did it. So this is how it looks like. So you already know that you know the answer for any initial condition. So if your initial condition is in here, then you will go to x equal to infinity when time goes to infinity. If you are in this point, maybe just a little bit to the left, then you know that you will have an unstable system, because as time goes to infinity, you will go towards the attractor, which is the origin in this case. So for any initial condition, you already know the evolution of the system when time goes to infinity. So this is just a summary to gather the knowledge we have already now. So this is simple. We have repellers. Therefore, in that case, we will have a Jacobian. In this case, two eigenvalues, because we have two dimensions. So in this case, the Jacobian, the eigenvalues will be positive or negative. Yeah, they will be positive. And the attractors is actually the contrary. They will be negative. And in the case we had just as well, in the previous example, we have saddles. So the eigenvalues are positive or negative. Actually, one is going to be positive and one is going to be negative. And the centers, as I already said it as well, have an eigenvalue that, or two eigenvalues that are imaginary. So these cases are robust. So if you have a Jacobian giving you this kind of information, you can be pretty sure that you will have repellers, attractors, or saddles. In here, in this case, which are borderline cases, you have a center, but if the system have strong nonlinearities, you may have situations that these strong nonlinearities perturb the center, and the center is not going to be anymore a center. So this is not a robust case. Now we go to this example, rabbits versus sheep. And this is a very nice example when we have actually two different populations that they are fighting for survival. So remember that we had this bad worm case when we have the predators that were controlling the growth of this population. So that was like somehow a one-way coupling. So the predators perturb the population of the bad worms. In this case, this is like a two-way communication. The rabbits perturb the population of sheep, but also the sheep somehow influence the population of the rabbits. And as a first modeling approach, we have a logistic growth. Again, so this is something we already saw. So from this example, you can remember that the carrying capacity is given by this number in here. So this population isolated, let's start, these are isolated first, which is going to have a larger number of individuals at the end. Yeah, this one, because the carrying capacity is larger than this one. So if you plot the model, so x with respect to time, and here y with respect to time, you will see the logistic growth. So we have a small increase, then a fast, and then it goes somehow to an asymptotic that is given by the carrying capacity in here. Okay. The nice thing is now to see what can we add so that these two models interact. So what is the trick? We need to connect these two. And this is how it is done. So right now we will add just an additional term in here and in here. So you can actually analyze that in here already we have a y. So let's come put in here there is a y coming into the game. And here we have x coming to the game. Okay, now we have to analyze first, we have to analyze two things. First of all, the sign is going to be a plus or a minus, and the second is the weight. So we multiply this y by a given number depending on how we perceive this interaction of the two populations. So let's start with the rabbits. The rabbits will actually be affected in a negative way if we have the presence of chips. So therefore, the first thing we have to see is that this is going to be a negative number. And the number in here, let's put, let's put k1, and let's put here k2. These are like weighting factors for y. The other thing is, okay, this sign is also negative because they are somehow like fighting. They do not somehow collaborate, but they somehow destroy themselves. The other question is k1 and k2. They are the same number? Well, actually this number is not the same. If you have one rabbit against one chip, who's gonna win the fight, let's say? Fight in terms of getting the resources of the ecosystem for survival. So actually the sheep, because the sheep they are larger and they are maybe stronger as well. So the only way that the rabbits somehow defeat sheep is that they grow faster and they are a larger number at some point. So in this case, we need to see that K1 under this model is larger than K2. Okay, and just based on data, we'll just have this relation. We'll have here a 2 and here we have a 1 and we have the negative signs. Just note that this equation is reorganized, so the x was here and now the y is goes here. Okay, so now the question, what do we do now? What is the step we have to find out? Yeah, so the first thing we have to see is to find the fixed points. How will we find the fixed points? Yes, by equating this equation to 0 and this equation to 0 as well. So let's write it down. We start this x3 minus x minus 2y is equal to 0 and y2 minus x minus y is equal to 0. So each equation has two roots. So the first one, here is pretty simple. We have x star, so fixed point 0, and this one is 0 as well. And now we have the other two equations, so we just write them here. Voila. Okay, we have to solve this equation. So let's go and say that y is equal to 2 minus x because of the second equation. And then we introduce this in the first equation. Then we say 3 minus x minus 2, and then 2 minus x, and then we just somehow derive the whole expression. So we continue, we say 3 plus x minus 4 is equal to 0, and then x is equal to 4 minus 3, which is equal to 1, which means that x is equal to 1, and therefore if we just see this equation in here, then y is equal to 1 as well. So let me just write in here the fixed points. We are obtaining fixed points. So the first one, what that we obtained was 0, 0. Now we have 1, 1. And my question is, this is all what we have? Actually, we have 2 more fixed points. And this should be actually clear. Then let's do it. We have, this is the equation 1, this is equation 2. So we have a possibility that x is equal to 0, okay? So if x is equal to 0, the first equation is going to be just, well, doesn't give us any information. But the second equation is going to tell us that y 2 minus y is equal to 0, and then we find that one solution is y equal to 0 and the other solution is y equal to 2. So this is another fixed point we have to take into account. Then this is 0, 2. And then we have the other situation when we have, we know that y is equal to 0 is a solution. Then the second equation doesn't give us any information. We go to the first one, and it's gonna be x 3 minus x, okay, because y is 0. And again, here we said that the first solution is x equal to 0, and the second one is x equal 3. So here we have the other one is 3, 0. Okay, then what is next? We know the fixed points. What do we want to do now? Finding the role of each fixed point, or the stability of each fixed point. Then we want to find what? The Jacobian around each fixed point. This is the first thing we will do, okay? So let me just write again here. So fx is equal 3x minus x to the square minus 2xy. Okay, this is actually fxy. And we have now gxy is equal to what? 2y minus xy plus y to the square. And what is the Jacobian again? So let's hide the general expression in this case. So it's the f, the x, the f, the y, the g ds, the g dy. So what is the f, the x? 3 minus 2x, minus 2y. Very good. What is the f dy? Yep, minus 2x. And now what is the dx? This is 0 minus y here, and the dy 2 minus x plus 2y. Okay, I just realized I flip a sign there. I don't know why I keep doing this, but it's good so that I hope you have already found out this silly mistake. Okay, so this is supposed to be a minus. Okay, so now we have the Jacobian, the general expression. Now we need the Jacobian for each fixed point. So we have g00 equal to something, then g11 equal to something, g02 equal to something, and g30 equal to something. So let's start with the first one, g00. This is simple. So what is the first term? The first term is gonna be 3. The second one is gonna be 0. The third 0. The fourth 2. Okay, now let's go with the second one. This is going to be 3 minus 2 minus 2, which is minus 1, then minus 2, then minus 1, then 2 minus 1, 1 minus 2 minus 1. Very good. Now let's go with the third one, 0, 2. So we have 3 minus 4 is equal to minus 1. Then this is 0. Then we have here minus 2. And then we have 2 minus 4 minus 2. Finally, we have 3, 0. So the first one is going to be 3 minus 6. 3 minus 6 is going to be minus 3. Then here we have minus 6. Then we have minus, this is 0. And the other one is 2 minus 3 minus 1. So in this part in the course, normally what I do is that I separate you in groups and 4 groups, and each group is responsible for a fixed point. Then you have to find first what? You have to find the eigenvalues of these 2 times 2 matrix, so 2 eigenvalues, and the corresponding eigenvectors. And with these 2 eigenvalues and eigenvectors, then you find the sketch. So these eigendirections and the direction, so if it's pointing inwards or outwards from the fixed point. And that's all. So this is what we did already. But now the cool thing is that now we have 4 fixed points. So this is gonna have like you will start building like the structure of your phase plane. Okay, we are in this virtual class now, but we will try to do the same thing. Okay, so right now I will stop this exercise, and I will assign you, I will assign you each of these matrices, and then we will go, and with MS Teams we will use this whiteboard app so that we can draw at the same time, or let's say at least in the same paper. Okay, and we will sketch this and we will have this prepared for the class. So the exercise finishes right now. Okay, it's gonna be incomplete. We will complete it all together. So right now we'll continue with jump, just the whole exercise. So we don't need to, well, the idea is that we will plot it together to understand every single detail in the first portrait of how this is built, okay? But now, so this is gonna be done together in the class. Right now we will start from the already built first portrait to interpret it. So we have how many fixed points? We have 4 fixed points, and we have, this is what, so you have to look at the again directions. One in the again direction that is behaving as an attractor, one that is behaving as a repeller. So this is a saddle. Here the 2 again directions are attractors, so this is an attractor, and this one is going to be a repeller. Okay, now we will introduce something called bassin of attraction. When we have a region, so you see that all this region in here, all this region, so the one that is in blue, is gonna end up being completely related to this attractor. What do you mean? What I mean is any initial condition in any of this region will go as time goes to infinity to the attractor in here. If you are in the white zone, instead of going in here, you will go to this attractor in here. So this is divided by this point, by this line here. And this is recognized, so this is called a separatrice of the basins of attraction. Okay, so this is how you interpret the phase plane right now. Now let's analyze it a bit in terms of physics. So what is actually this representing? Do you think sheep and rabbits, can they cohabit? Can they live together in peace? It's gonna be pretty actually hard. Indeed, what this model is telling us is that there is the principle of mutual exclusion. So at some point, you will have a given amount of rabbits and a given amount of sheep, yes, but this is going to be just an instant in time, because when time goes to infinity, then everything will go, in this case, balance towards the rabbits. It means that the rabbits is gonna populate the whole ecosystem, and sheep will completely extinguish, will disappear. But also we can have the opposite scenario, when we have actually only sheep and just rabbits being completely out of the picture after a given time. Something then to see is the importance of the initial conditions. This is critical. So imagine first that this model actually is robust enough to describe reality. This is the first thing. And then let's assume we have to do an experiment and we have a forest, and we just introduce here at this moment just a given amount of sheep and rabbits. So if you just wait a bit at just the very beginning, sheep or rabbits, depending on the amount of individuals for each population you just introduce, you completely define the future. Interesting thing. And this is something I would like, maybe as we are having some nice time at home to do things, interesting things, this can actually be also a model for competition in this our society ruled by capitalism. So I'm wondering how close is this model to, for example, describe the phenomenon of monopoly. You will have a lot of, let's say, fair competition at some point, but at the end of the day, there are always one company that absorbs others. And this is interesting, and I'm pretty pretty certain that a model close to the one we just saw may describe this phenomenon. We can discuss this in class. Okay, we will just now talk a bit about conservative systems. So remember that when we were in one-dimensional systems, so we have a particle like going along a trajectory, so just following a line. And we said that it was necessary that the energy, the potential, decreases all the time. And it will decrease until finding a minimum in the potential function. And this minimum is actually related to a fixed point. Maybe you already remember that. In two-dimensional systems, we may have these situations, of course, but also we can have a system that is conservative, which means that you just go along a trajectory. Imagine an orbit, imagine this center. So the center is actually describing the pendulum without friction. And the particle just move along this center, along this circular trajectory. But the energy is constant, it doesn't change. What does it mean? That the particle will move forever. So it's not going to be just reaching a equilibrium in terms of no motion. Okay, so we start with this equation. So we will describe the equation with this in Newton. So m times acceleration equal a given force, and this force is a nonlinear force. And in the same way that we describe the one-dimensional system, we can see that these df's can be related to a potential, so that is written in this way, minus dv dx. Okay, so let's just do some playing around and see what we get. So we have m x dot equal 2 minus dv dx. And we also know that dv dt, so we want to know the change of potential in time is just given by the chain rule dv dx dx dt. So this is maybe just not to so this is actually x dot, no? This is just to remember. Okay, and then we have dv dx is just m x dot here, and this is x dot there. Now we have to play around with these two terms. So basically we will apply like a derivative rule. So we have dx, imagine you have something like this, dt. So you can say that dx, and here dx dt, so 2 times x. You can say that this is equal to x dot dx dot t plus the same thing, okay? This is actually 2x dot, and this one is nothing but x dot dot. Then you can see actually that x dot is equal to 1 over 2 d t x to the square. So this is what we just did in here. So okay, let me just do a line there. So dv dt is equal to m x dot x, which is equal to m over 2 dt x dot square. So the idea is that we will just reorganize the equation and we will say that dv dt phi in here is minus, oh god. Okay, you may think that I do mistakes intentionally. Some of them are intentional, some of them are not. So right now it's like a, okay, I will you see, guess. I did a mistake, and this is actually pretty important, and maybe I do mistakes so that you actually remember not to doing them, hopefully. So I just forgot this sign in here. So this is gonna be put in there, and therefore in there, and therefore in there, okay? Which means we have a minus sign in here and a minus sign in there. Now, if we reorganize this equation, we will have d dt, the potential, plus m2 x dot square. And this is going to be 0 because we are reorganizing the equation. But also it means that we will have something that we can define as energy to be constant. So this is going to be a constant quantity. And this is what happens in the terms of systems like the pendulum, which are conservative. So we have this system, for example, which is the pendulum. Then the idea of interpreting this is that the particle is going to go always along these trajectories and will remain them there forever with constant energy. Okay, let's talk now more, let's say, directly about the pendulum. We know that the pendulum is a conservative system, therefore we have this is our definition. We have kinetic energy expressed like this, which in terms of the figure of the pendulum is maybe more clear when I talk to you about this v velocity, which is actually the tangential velocity, like this. We have an angle theta, we have the distance projected with this angle, and also the h. And this h is what defines the potential energy in here, mgh. Now we add the potential to the kinetic energy, and we know that they have to remain constant, which means that the derivative of ek plus ep has to be 0. And this is what we do here. This is the derivative of the first term and the derivative of the second one. And this is just some simple calculus, and we arrive to 0. So by doing this approach, so this is like an energetic approach. You can also have the potential, the equation for a pendulum in terms of a balance of forces. But right now we just follow this approach, which is also pretty interesting. And in here you should see that if we factorize t dot, then we have ml t dot plus mgl sinus of theta. And this is the equation that we are interested in. So just by reorganizing some terms, we end up having this equation. Okay, so what do we do now? The same thing as always, we find the fixed points. But before finding the fixed points, we have to convert this equation into a into two first order ODEs. So we have this in here. Once we do that, then we can find the Jacobian. So the Jacobian is going to be given by this term. So you can just already see why. So you can just derive it by yourself. It's nothing super complicated. And something that I just forgot to say, the fixed points. What are the fixed points in here? Are this nu equal to 0, and also sinus of theta 0. Okay, that's why we will have theta being just 0, p, pi, 2 pi, and so on. So that is what we have in here. So as in the example of the previous slides, we just replace for each fixed points we obtain a Jacobian, and then let's select 3 fixed points. We will select minus pi, 0, 0, and pi 0. Let's find now the eigenvalues for each Jacobian. So just remember again this formula. So from here it is obvious, or let's say it's simple to realize that the question simplifies because the trace, what is the trace of this matrix? Well, actually all the trace of all the matrices is 0. Okay, so we will end up having just to deal with the determinant, which is this delta, and the determinant is, so delta is minus GL, here is GL, and here is minus GL. And now remember this sign here. So which of these one has to deal with imaginary numbers? Actually this one. So this is the one that contains an imaginary number. So we can just obtain the fixed points. So this is like this. So we have two fixed points, two eigenvalues for each Jacobian. So the question for a lambda that is pure imaginary, do we have a saddle, a stable node, or a center? Think. Yeah, this is something we already discussed. Then we have a center. In this case, we have a saddle, because we have lambda, they are real, but they have different signs, and it's the same case for the other one. So we have a saddle, a center, and a saddle, and this is how you picture it. Then you just have the corresponding fixed point, which is a center, and the corresponding trajectories going around it, and the eigendirections corresponding to the saddle. Okay, so these eigendirections, remember, you just find them by computing the eigenvectors for the Jacobians, and then you just fill the gaps. So when you fill the gaps, this is what happens. And right now we will be able to understand these pendulum animations I showed you in the first session. So let's go. So let's now concentrate in this little like perturbation on a given pendulum. So we have a little angle theta, and this is the trajectory we're following. Okay, so this is somehow here stretched, but this is a circle. So this is what we obtain. The pendulum will just move like that forever. We don't have friction. Okay, now what happens if you increase the amplitude of the oscillation, so this theta. So right now we just have a stronger amplitude, but still we move along a, okay, this is not anymore a circular trajectory. You can see here that is a little bit like an ellipse, more or less. Now let's increase even more this amplitude. So in this case we will be very, very, very close to this trajectory. So this is the shape of the trajectory, and if we just do play, we see that we are approximating the other fixed point. So the other fixed point is, remember, a saddle. So we have it in here. So we're moving like to this, and you see there is like a sort of deceleration when it goes in these points. So here you can see in here a little deceleration. Okay, now what happens if we go just in there, very close to this? Okay, before keep talking, you have realized already that I have talked about this trajectory already many times. This trajectory is becoming very important in the description of the pendulum. Okay, so let's give it a name already. This is going to be a saddle connector, and maybe a more fancy name that it has is heteroclinic trajectory. So what happens if we are very close to this heteroclinic trajectory? I will just put play. You will see that the pendulum is whirling around, but is getting very close to the other fixed point. The other fixed point, remember, is a saddle, so in here and in here, but still, I mean, it is not on the heteroclinic trajectory. Ideally speaking, is it possible? So if you were actually standing on the heteroclinic trajectory, you will be reaching asymptotically the other equilibrium point, which is this one. So you approach it like with an exponential decay. So eventually you will be able to reach the equilibrium point, but you are actually standing on the heteroclinic trajectory, which is in reality not possible. So this is like a separatrix again between the scenarios when your pendulum is not able to whirl over the top, with the scenarios where the pendulum is always turning and turning and turning. And this is what we'll see just now in the other little animation. So in this animation, you will see that just above this heteroclinic trajectory, we are now turning forever. So it decelerates a lot when you arrive very close to the other equilibrium point in here, but then accelerates and will be there forever. Remember, this is a conservative system, therefore the energy remains constant, and therefore this is gonna move forever. Okay, ladies and gentlemen, we have a very rich amount of scenarios when we make a pendulum turn. And this is just described in a very precise way by the phase plane that we have in here. This is again a conservative system. What happens if we add a little bit of dissipation? What happens? So you will see that all centers become spirals, and the phase protector will be a little bit like flipped. So I will just show you in the next slide. So we're adding this term in here, and that's what we obtain. So you can already picture in your minds what is going on. Imagine you you have a very strong initial condition. I will just draw here the pendulum, and this is gonna be the red point. So if it's very strong, then you will see that we will follow, for example, this trajectory in here, and then we are somehow trapped. So again, we go very fast at the beginning, then little by little, every time you have a strong deceleration, and at the end we will just get trapped by a given loop. So in that sense, we will somehow represent this by turning, and then at some point it just doesn't make the whole turn, and little by little it will decay until the equilibrium point. So as you just saw, centers become stable spirals and saddles remain saddles. So the saddle didn't change. Although note that we don't have any more saddle connections. Okay, so we are done with the class of today of the phase plane. So just go through. You know that we have some incomplete exercises, so we will do that together in the next class. And then we will just go into the next video about limit cycles. This is a pretty big content, so we will do it in two parts, A and B. And okay, I hope you have enjoyed, and see you next time. Bye bye.